started. Everybody, settle down, settle down. Let's get started. First off, let's talk about scheduling. So, I know I owe you all a couple of homework assignments. I spoke with my TA. He's going to try and get you the homework 6 assignment graded, hopefully by Wednesday. He's got a homework assignment in concrete. He's got a grade as well. As soon as I do, or give him that, homework 7's going to him. So hopefully we'll get that back soon as well. Homework 8's due on Wednesday, so those are the only outstanding assignments. In terms of other logistics with the grades, exams 1 and 2 are graded in here, so the only other exam we're waiting on is the final. So we should be rocking and rolling. Here is the calendar for the rest of the semester on the homework assignments. You got homework 8 due on Wednesday, which I'm going to open it up for questions here in a second. Then homework 9 is due our last day of the semester. Before I open it up to homework assignments, I do want to talk about the course evals. We've changed the calendar at Marshall this year, so next year we actually lose a week. We have 15 weeks and the finals this year. Next year will be 14 weeks in the final. So because of that, I'm sort of taking that to heart a little bit. I'm going to do some surgery to this class as well as concrete and structural analysis. Like I can tell you, structural analysis, I'm doing some pretty significant changes to that course. But the reason I mention that is because of the course evals. If you all have any suggestions for like future classes or any improvements or anything like that, I really do listen to it. So I really do want everybody, bless you, I really do want everybody to do the course evals. Bless you again. So right now, I saw that one person's already done them. I did the same thing I've done in previous semesters. I opened up a slot on Blackboard for you to just upload a screen capture that just shows me that you did it. If you do that, and just upload the screen capture that you did it, you can say I'm the worst professor ever and rank me over the coals. I just want to see that you've done it. You get 10 bonus homework points. Does that mean you can have a homework average higher than 100%? Yes, you can. So yeah. Sound good? Now, I've gotten a few questions today about homework number 8. So I get the feeling that there are a few doubts or a few questions. Are there any questions about homework 8? I can go ahead and respond to a few of them. There was one question about problem number 3, and there's a statement in problem number 3 about the framing. It states that the dead load includes the self-weight of the framing. That's just another way of saying the self-weight of the beam. You don't need to assume a beam self-weight because that dead load that's specified incorporates the beam self-weight. You don't need to account for that. So yeah, that's the only other. I mean, there were some specific questions about problem number 2 about how to do deflections, but I mean, they were really specific. I don't know if there's anything general that I can relate. Are there any questions about the homework? Have you looked at the homework? You should. Everybody, to the ones that have looked at the homework, just started chuckling. So, any questions at all?
Maybe this is a stupid question, but on problem 3, the live load says assume that the load is already reduced. The live load, is that just at a particular point? Is that all the way across the beam?
Neither. It's a pressure load.
Okay. That's good.
Remember, if you have, let's say, 200 pounds per square foot, and it's applied over a floor system, and the beams are 8 foot apart, so you take 200 pounds per square foot times 8 foot, and so that's 1.6 kips per foot along that beam. So it's a pressure load. It's neither a distributed load or a point load. And for those of you that have not had concrete design, that statement about live load reduction or anything being reduced, just ignore it. That's for the folks that did live load reduction early on in concrete design, and I'm just heading off questions before they come, so don't worry about it. Like from the Wizard of Oz, pay no attention to that man behind the curtain. Wizard of Oz? You've seen the Wizard of Oz, right?
Yes. Showing your age, Dr.
You're shaking your head no? You've never seen the Wizard of Oz?
And me too.
Listen,
No,
don't
seen either.
take her into account. I've tried real hard. She had the same problem.
See, I generally hate musicals, and I've seen The Wizard of Oz.
See, if it's come on like Lifetime or Hallmark, she's never seen it.
All right. Your time in the spotlight, we'll move on. I mean, but come on, this is pop culture. This is coming from the dorky engineer. All right, settle down. Okay, so, everybody settle down. So, this is where, let me say this. Today we're going to finally talk about discretely braced beam capacity, and I'd argue that this is probably the lecture where we finally just reveal, what's going on with capacity. We've been sort of dancing around it for a really, really long time, and I kind of want to just, pull back the curtain and say, all right, here it is. Before I show the curve, I do want to just remind everybody what we had concluded last time. So we had concluded that the curve was going to look something like this. We have LB on this axis. We have MN on this axis. There were a couple of things that we had concluded before we even drew the curve. We said that right here, when LB is 0, what is MN? What is M going to be? We had already done this. MP, the plastic moment. Because when the beam is fully braced, when LB is 0, its capacity is the plastic moment capacity, right? We had already determined that. And the second thing that we had determined was, as LB increased, what happens to the capacity? Does it go up? It goes down. So generally, the curve should go down from here. It should generally get smaller. Well, that's exactly what happens, okay? And so, let me just sort of illustrate. This is what the curve looks like, okay? Now, there's a lot going on here. Don't worry, we're going to chop away at this, really, really explicitly. But let me sort of explain what's going on. So, what the spec does is it splits the capacity up into 3 separate zones, okay? Now, I'm going to redraw the curve here on the board. And I'm going to sort of explain verbally what's going on here on the slide so you can kind of see the difference and what happened. Okay, so first off, let's keep in mind, let's just go back to, make sure everybody understands what's going on with the graph. So here on the x-axis, this is the unbraced length. Now everybody remembers what that term unbraced length is. If I have a beam, it doesn't really matter what's going on with the boundary conditions. LB is how far apart your braces are, right? So what this is saying is that the farther apart the braces are, the weaker the beam is going to be. Okay, so first off, what the spec does is it defines 3 zones of beam behavior. Okay, now this first zone over here is what we're calling essentially the MP zone. Okay. So let's keep in mind, this is a zone where the unbraced length is really, really small, right? Everybody see what I mean? This is where the unbraced lengths are really, really low. So if you wanted an image of what this beam looks like, here's the beam. It's a beam with braces all over the place. So a lot of braces framing into that, okay? So because that beam is really, really braced and it's really, really constrained, it's not going to kick over to the left or right, we say, you know what, that beam is going to be able to reach MP. And where do we cut that off? We say anytime that the unbraced length is less than this anchor value, L sub P. So there are 2 anchor lengths. There's an L sub P and an L sub R. Okay, so that's the plastic moment. Now, as for these other 2 zones, let me sort of remind you of something. Do you all remember this curve here? So this was KL over R, this was F critical, and the curve for a column looked something like this. So that point was 4.71 times the square root of E over Fy, and then this was 0.877 Fe, and this was 0.658. Y'all remember that? That should be familiar from college, right? Okay, so how did we define that verbally? I think this marker's down on me. How did we define that verbally? We said that this was the inelastic range, and this was the elastic range. In other words, everything to the right of that limit is when the column behaves like a rubber band, and everything to the left of that limit is where the column starts to behave like the crushed up soda can. Like you crush it and it doesn't go back to the way it was. Remember that? So there's the inelastic range and the elastic range. Well, it's the same thing here. For this second zone, we have inelastic buckling, and for this zone, it's elastic. And the buckling that we're talking about is lateral torsional buckling. So maybe I should write that as LTB. Okay. And so there's nothing here on the board that's not here. I'm just sort of breaking the curve down a little bit more sort of explicitly so that you can kind of understand what's going on. Okay? Now, what's going on, a couple other things that are going on with this curve, and so that you don't feel that what we've done so far is a complete waste of time. This region here, this curved region, this is that diffie-q derivation that we derived. That diffie-q that we derived where we assume the sine curve and plug and chug and solve for the moment, that's that elastic LTB curve. So if you're wondering where that equation came from, it came from there. Okay? As for this straight line curve right here, that's just the folks who write the spec trying to make inelastic buckling really easy. We basically say it's just a straight line fit between MP and this value right here. And this value right here, basically, it's 0.7 times the yield moment. Okay? So this 0.7 times the yield moment, we have a name for that in the spec. We call it M sub R. So why do we call it M sub R? Well, the reason why is basically this is the yield moment that has been reduced to account for the presence of residual stresses. Okay? Remember that whole residual stress thing? Remember there's geometric imperfections and residual stresses? Well, that's how the spec is handling that. And so that's just residual stresses. Okay? And that is basically the beam capacity curve in a nutshell. As the length gets larger, the capacity generally gets smaller. But specifically what we have to do is figure out whether or not we're in one of three zones. Are we in zone 1 where our capacity is just MP? Are we in between where we're in inelastic? Or where are we in elastic range? I will go ahead and tell you that by and large, the vast majority of beams that we design are probably going to fall within zone 2. Okay? So just so everybody's aware, that's what zone 2 is. Okay. Sound good? Now, there's one thing we're not talking about, and that's C sub B. Now remind me, C sub B values, do they tend to be larger than 1, or do they tend to be smaller than 1? Larger than 1. So this whole curve is derived based off of a C sub B value that equals 1, but really that's punitive. Steel beams can generate capacities far above what they would get with C sub B equals 1, and that's what C sub B does. So I want y'all to watch up here. Okay, so here's just the standard curve, and this is what happens when you apply C sub B, is that the curve gets bigger. Okay, C sub B is larger than 1, so the capacities get bigger. But here's where you got to pay attention. I don't really give a damn what C sub B does. The capacity is always cut off at M sub P. Okay? So C sub B is a really powerful tool in that it can augment your buckling capacity to account for that non-uniform moment. However, it does have one limit, and the limit is that used improperly, it can magnify capacities above MP. I don't care what's going on MP is the maximum bending moment that a beam can withstand, period. So all of the equations that we're going to see here in a second all have a limit. They basically say the capacity is the minimum of this pile of junk, or MP. Okay? And that's why, because C sub B can serve to falsely augment the capacity accordingly. Now, just so you're aware, I'm going to show you all a bunch of equations. You don't have to worry about marking them down because I got a nice little guide at the end that summarizes everything you need to know. So don't worry, but I'm just going to walk you through it. Okay, is everybody with me so far? Don't worry, we're going to define the terms explicitly, but everybody with me so far? Okay, now, if you have a beam, and this is your unbraced length, the first question that you're probably going to ask is, well, am I here, here, or here? And that depends on what LP and LR are. Now, I'm going to tell you, this LR equation is probably the nastiest equation in this entire course. That's the equation for LR, and that's the equation for LP. Now, first off, don't worry, you don't have to compute them. I'll show you why here in a second. But what's even funnier is, let me ask you a question. Of those two equations, which do you think is the toughest to derive? LP or the LR? The LP is actually the toughest, okay? The LP requires a lot of testing, a lot of data analysis, and a lot of, you got to do you got to put some thought into figuring out which is going to govern the capacity. LR, while it looks nasty, is really just an algebra problem, because all we do is we set that Diffie Q equal to 0.7 times the yield moment and just solve for the length. And so, does it look nasty? Yeah, it looks nasty, but it's pretty straightforward. Now, this LP and this LR distance are can be some fairly laborious calcs. Fortunately, you don't have to do it. Remember the ZX table? LP and LR are already computed for you, so you don't have to go out of your way to start chugging out of LP and LR. They're right there. Okay, so I'm telling you, this ZX table is probably one of the most valuable tables in the spec. Not only does it calculate LP and LR, it also calculates MP and MR. So you've got this value and this value computed for you. So that's a pretty worthwhile term. The only one that isn't quite described yet is this BF factor, but it's a lot easier than you would think. Okay, so let's get into the math. So essentially, like we said, we have three zones. We have zone 1, where the capacity is the plastic moment. Zone 2, where it's inelastic buckling somewhere between LP and LR, or elastic buckling where it's greater than LR. So the second zone, zone 2, is just a straight line fit between MP and MR, and then zone 3 is the same as what we derived earlier, that Diffie Q derivation, same as before. Now, here is the equation for zone 2 that's straight out of the spec. We're actually not going to use the equation in this form very often. The reason why is there's a shortcut that we can use to describe this one and make it a lot more user-friendly. The one thing I do want to point out is a lot of these equations are going to be the nominal moment capacity equals a pile of junk less than or equal to MP. And remember, what that's saying is that it's the minimum of those two terms. Okay? The reason why we have the minimum is because of that false amplification. Remember, the capacity is whatever this pile of junk is multiplied by CB or this. Remember, your capacity can never be larger than MP. Okay? Now, like I said, we're not going to use the equation in this term very often. We're actually going to use it in this form very often. This is a lot easier. And so the way that we do that is we take this expression, we rewrite it a bit, we take this term here and move it into this fraction, and I take a look at this fraction here. Let's take a look at this. So MP minus MR over LR minus LP. Well, LR minus LP, that kind of looks like a change in X. That MP and MR, that kind of looks like a change in Y. the slope of this line is this term BF, okay? So if you're wondering what that BF term is, all it is just the change, the slope of that line. It stands for beam factor. I know that we're really creative as structural engineers. And again, BF terms are listed right here. And they're already factored, so you don't even need to worry about it. Yes, sir?
If you were calculating braces for a bridge and you're using a steel plate girder,
Mhm.
you have to calculate all your LPs and LRs by hand because you don't have to.
Yeah. And that's where, the short answer is yes, but that's where the beauty of Microsoft Excel comes into play, because you build a spreadsheet, you compute it once, you never have to do it again, just plug in your numbers and it does all that. So yeah, I'm showing you the equations for that very reason, that if you're ever looking at a plate girder or some shape that's not defined by the spec, bless you, and you're going to have to grunt it out, it's all here. And here's the thing, you don't even have to have the slides for it. It's all in chapter F right here, so it's not like I'm showing you anything that's not in the spec. Bless you. That answer your question? Everybody else good? Okay. So zone 2, we've got this really nasty equation, but we can take this equation and make it a lot easier here through the use of this beam factor, which has already been calculated for us. Zone 1 is really easy to compute. Zone 2, really easy to compute. Zone 3 is the only one that we kind of have to grunt out a bit, and the reason why is because there just isn't a shortcut for this equation here. It's the only one that we just kind of have to roll up our sleeves and just do it. Now, there is, I am lying a little bit, there is a comprehensive design aid later, but we need to walk before we can run, and so right now, just trust me, it's a lot easier to just grunt your way through this one. So, if you want to put a nice little star or bookmark or everything around slide 440, that would be a good place to do it, because I'm summarizing all your equations in one nice, neat, concise scenario. So zone 1, the capacity is MP. Zone 2, it's either the straight line fit or MP, whichever one is smaller. Zone 3, it's either MP or this expression here. FCR is that. There's your C sub B equation. And all of these new terms like LP, LR, the beam factor can all be found in the CX tables. This is one to definitely put you a bookmark on in your notes, what have you, you name it. Okay. Now, does anybody have any questions? Yes.
What's an RTS version?
RTS. RTS is sort of like a radius of gyration for LTB, and it's a lookup. And we're actually going to investigate that in this example, so don't worry. You'll understand how these expressions work pretty shortly, or really easy. Everybody good? Okay. Now I'm showing a bunch of equations up here and a bunch of formulas and variables and all that. I kind of think that it's worthwhile to just sort of grunt our way through it and do it. Okay. So I have a beam here. We're going to say it's 24 by 76. We're going to say that it's simply supported and it's going to withstand a concentrated load at midspan. So here's the beam. Okay? Now, the beam is laterally braced at its supports. I got a brace here, and I got a brace here, and I have a brace at midspan, okay? And it's going to withstand some concentrated load right here, okay? Now, this statement here, this second bullet, is really it's really important for our problem. We're going to assume that the self-weight of the beam is negligible, okay? There's a very specific reason why. If I assume that the self-weight of the beam is negligible, what does the moment diagram look like? Say it again, or you're both saying the same thing. Well, you're saying that. Is that right? Me. I'm going to have a reaction here. What's my shear diagram look like? Up, over, down, over, up. So what's the moment diagram look like? Is it rounded?
It's
Linear. There we go. It goes up and down. Right? Y'all remember that? Here, this is really important. I really want everybody to pay attention to this. I want you to turn in your manual to 3-18. For those of you that brought your AISC 15th edition steel construction manuals with them. Now, table 3.2 is the ZX tables. But what about table 3.1 for those of you that brought the AISC 15th edition steel construction manual? Tables 3.1 lists C sub B values for various simply supported cases. And if you have a beam that is braced at the ends and at midspan and it's subjected to a point load, what is your C sub B value? 1.67. And one of the things about C sub B is it's actually completely independent of the load. In other words, in this scenario, and I make this very clear, in this scenario. See, as soon as we start considering that this beam has, 1 kip per foot distributed dead load, those equations are all trash. In fact, to be perfectly honest, I really don't like using them very much for that specific reason, okay? However, in this example, I'm making it a point to neglect the self-weight, and the reason why I'm doing that is so that C sub B can be 1.67 for all of these cases. You all know how to compute C sub B because we had a much more difficult example than this one last time, and C sub B, I think, went pretty smoothly. So is everybody okay with that? So probably the most important simplification on this problem is assuming that the self-weight of the beam can be neglected.
So if the self-weight is not neglected, you have to calculate C sub B.
Yes. Because this isn't your moment diagram. That's why. This isn't your moment diagram. It's going to be this plus some distributed load. So the C sub B value is going to be modified. Does that make sense? Everybody okay with that? Okay. Now, on the flip side, if all you have on the beam is distributed load and you don't have anything else, just distributed load, these cases here on the bottom are just fine. Because again, if all you have is one load type, the magnitude of that load doesn't really matter. Okay, so what we're going to do for this problem is we're going to compute the capacity for each of these different cases. So I'm going to take it one step at a time. Make sure everybody's clear with what's going on. All right, so example 23. So first off, from table 3.1, C sub B is 1.67. So that's going to be a simplification. Now, let's look up some properties for this 24 by 76. Now, I didn't tell you what the yield strength was explicitly for this example. However, when I don't tell you what the yield strength is for a W shape, what is the preferred material spec for a W shape? A992. What's the yield strength for A992 steel? 50. So if I don't tell you, that doesn't mean you can't assume the most reasonable value to move forward. In fact, I may not tell you. See what you come up with. Now, we're going to need some values. So first off, let's everybody turn to table 1-1 and let's look up the W24 by 76. Now, you're not going to need every property, but I'll help you through the ones that you will need. Now, has everybody found the 24 by 76? Page what? 1-what? 1-18. So if you aren't on page 1-18, hit page 1-18. If you brought your AISC 15th edition steel construction manual. I'm looking at some folks who don't have theirs out. All right. Now, instead of writing down every single property that you would ever need, I'll walk you through what we will need. We're going to need SX. We're going to need H0. We're going to need RTS. And we're going to need J. Now I'll define what each of these are here in a minute, but let's get the values first. So what's SX? 176 what? All right. H0. 23.2 inches. If you're curious what that value is, all H0 is if you have an I-beam, H0 is from center of flange to center of flange. That's H0. That's all that is. RTS is the radius of gyration for torsion, for LTB, for lateral torsional buckling. And so what does that come out to be? 2.33 inches. And what's J?
2.68 inches to the fourth.
Okay. All right. So the next thing that we're going to need to look up some values from table 3.2, the ZX table. Which that's another thing. I'm just going to forewarn you. When you're doing beam analysis and design, I'd say that beam analysis and design, more than anything, involves you flipping back and forth from table to table to table, and it just sort of is what it is. Now, some of these guides try and do a good job of like not making you do that. For instance, the ZX table also lists the moment of inertia and things like that, but it just sort of is what it is. All right. Now, table 3.2, I'm going to get a couple quantities. What's the plastic moment? $750 what? All right. I'm going to get the beam factor. Now this is the slope of a line, and so you would multiply that times the x coordinate to get a coordinate on the line. So the units of that are actually in kips, because it's the slope of a line times the x coordinate. So what is the beam factor? 22.6 kips. So because we have MP and because we have the BF factor, we actually don't need PMR. We won't need that. But we will need LP and LR. What are LP and LR?
LP is 6.78.
6.78 feet. And LR is
19.5.
19.5 feet.
Why would we multiply BF by feet? Why is that BF?
Sorry, what?
Why is BF multiplied by feet?
Because here's why. That's a good question. That's a really good question. And the answer is basically because of this right here. In order to use table 3.2, so for instance, if we're using table 3.2, table 3.2 says, zone 2 is the minimum of this pile of junk or the plastic moment, but that's already been adjusted by feet. So if I'm going to adjust this by feet and this by feet, I have to sort of make sure I'm comparing apples to apples, which is why the beam factor values in table 3.2 are listed in both ASD and LRFD. So they are accounting for both. Because, see, this would be a better slide to look at. See, this is the simplification, but if I want phi in, I have to multiply everything. Does that make sense? I mean, this is a good question. Everybody good? Did I answer your question?
Yeah, that's something kind of like changing that slope, right?
Well, but you're multiplying this whole curve by phi when you factor it anyway. So this is going down, so you are changing the slope. I mean, think what would happen if you took this and you multiplied it by 0.9, just like what C sub B does. What does C sub B do? Multiplies everything up. Is everybody okay with that? Did I answer it? Everybody good? Okay. All right. Okay. Let's start getting into these cases. Okay, so here's the example. We have 3 cases. We have a case where the length is 10 feet, a case where the length is 30 feet, and the case where the length is 50 feet. So let's look at case 1. L is 10 feet. If case 1, L is 10 feet, what's LB? 5 feet. I want that to be crystal clear to everybody in this room, okay? The beam is 10 foot long, but I don't really care so much anymore. When I'm computing capacity, I don't care about how long the beam is. I care about the distance between braces. So the beam is 10 foot long. I need the beam length to do the structural analysis, but to compute the capacity, I care about this distance, and that distance is 5 feet. Does that make sense? So for case 2, LB is what? 15. And case 3, LB is what? 25. Okay. I'm not moving forward until I have a good idea that everybody understands what I'm talking about here. This is really important. There is a difference between the length of the beam, which you need in order to determine reactions, shears, bending moments, all that, versus LB, which is what you need in order to determine how strong the beam is. That's really important. Okay. All right. So let's take a look at case 1. Now I want you to tell me with case 1, so case 1, L is 10 feet, LB is 5 feet. Tell me, what zone are we in? What?
Fully plastic.
Fully plastic, yeah. So we're in zone 1. And we are in that zone because LB is 5 feet and LP is 6.78 feet. So LB is less than LP. And so here's our curve, and we're here. So this beam's got braces all over the place. And when the beam's got braces all over the place, what's the bending capacity? MP, right? So therefore, phi mn is just BMP. Does that make sense? All right, any questions? All right, zone, or case 2. So case 2, we have an L of 30 feet, LB of 15 feet. What zone are we going to be in? 2. Zone 2, because LP is 6.78, LR is 19.5, but we have an LB of 15 feet. Does that make sense? That we're between these two? So we're somewhere in here, right? So our capacity should be in this straight line fit, but don't forget we've got that C sub B value. It's going to rear its ugly head here in a second. So I'm going to go to the slide because I want you to see exactly where I'm getting these equations from. So when you're in zone 2, this is your capacity. I'm going to copy and paste this directly on the notes. There's your capacity. I want you to help me out. Is there anything in this equation that we don't know? What's C sub B? What's V and P? 750. What's our beam factor? We know LB and LP. So this is a plug and chug. So what was the beam factor? 22.6? So, what are we getting for this upper expression? What are we getting for this?
$942.26.
942.26. Do I have a second on that? That's foot kips and that's minus. I don't know why my minus in the way. Minus. Do I have a second on that? He said 942. Yeah. So what's the capacity? 750. And so the answer is also 750. And I'll explain what happened here in a second. So, okay, well, that popped up. So let me go back a couple slides just to illustrate. Remember this equation right here? Remember this expression here? Ultimately, what happened is we just did the math, and that 942 was a capacity somewhere right here, between LP and LR, but above MP. And remember, I don't care what's going on with C sub B, you always cut that capacity off at MP, and that's exactly what happened here. The computed capacity was well above MP, and that's what we got. Does that make sense? Okay. Last one is zone 3. If I could untangle this, I think you could probably see where this is going, because case 3, which is L equals 50 foot, LB is 25 feet. Well, LB is 25 feet, LR 19.5 feet. We're definitely in zone 3, right? That's pretty straightforward. And here's the thing. There is no nice, pretty little guide or aid to work your way through these equations. You're just going to kind of have to muscle through it. And so the way that you do that is you start off by computing FCR. And FCR is C sub B times pi squared times E times our slenderness squared, and then 1 minus 0.078 JC over SX H0 LB RTS squared. Okay. And so this is something that, quite honestly, everybody should practice and make sure that they're comfortable with, but there is something you got to watch out for. Okay? Let's look at this outside fraction. So what's C sub B?
1.67.
Pi squared. What's E? There we go. Now, what's RTS? 2.33 inches. So what's LB? Say it again.
25 times 12.
That's exactly right. LB is 25 feet, but that equals 300 inches. Units. Gotta match your units. So this is 300 inches divided by 2.33 inches. Don't forget to square it. So make sure that you're watching your units on that. That's really important. Okay? Okay. And so we have 1 minus 0.078. And then we've got a couple fractions. So what was J?
2.68.
Wait, what?
1 plus 6.
Yeah, I'm sorry. Hold on. Yeah. That was my fault. So I should have copied and pasted. I meant to copy and paste the formula. I should have done that. I apologize. It's still not 7. Not even. Okay. The C value, C is always 1 for I-beams, so you can almost just sort of ignore it. SX is 176 cubic inches. I'm doing on time. Okay, I got it. 1.76 cubic inches. H sub naught, 23.2 inches. So help me out. Inside the brackets, what are the units going to be? Unitless. In fact, everything inside this square root is unitless. Lastly, we have 300 inches over 2.33 inches squared. So if you look at the units, think everything under the square root, the units cancel. Down here, the units cancel. The only thing that retains units is whatever E was in. So it's KSI. And it's a stress. We're calculating FCR, so it's a stress. So you really ought to be comfortable with this calc, because this is feasibly one of the longest calcs you really could do. Not just for beams, but I'd say really in this class. This is probably the nastiest formula we've ever used in this course period. But not only that, it's probably one of the most nasty, or the nastiest formulas that we use in steel design period.
Sorry, what did you say the 1.0 was for with the JC?
That's a good question. So this is it's sort of a modification factor in the spec to modify this formula if you're not using an I-beam. But we're always going to be using I-beam, so we just take it to be 1. That's a good question. It's that, and then there's values for channels and whatnot. So anybody got a value for this?
29.0.
I got 39.2.
I think you're getting voted down. I got 39.2. That's what I got. 39.20. That's okay though. This is a nasty one. This is a nasty formula. So therefore, BMN is the minimum of phi F critical SX or phi MP. So the minimum of 0.9 39.2 KSI. What was SX? 176. Then the last thing we have to convert. Then we compare that against 750. And so they may have a value up top. Because this is going to come out in inch chips, so we got to convert to feet. So we'll call it after this. What we're going to have to. Right.
I got 517.44.
So 517.5. Anybody have a second on that? There we go. Okay, I know these equations were a little long, but is everybody okay with this? It's not too bad, right? There's no iteration or any, goal seeking or anything. It really is plug and chug. All right, hold on. Any questions? All right, just be clear. Wednesday, y'all have homework 8 due for me. And finally, when we come back on Wednesday, we are going to use this for design. That's all I have, everybody. I will leave this up. If anybody needs to finish writing, let me stop my recording. I'll see y'all on Wednesday.